Alright, so the problem that I decided to tackle is the birthday problem, and I came across this problem during a Deloitte information session. The guest speaker was talking about the importance of clearly thinking about problems, and he posed the question of what we thought would be the minimum number of people that we needed to have in a room in order to guarantee at least a 50% chance of two people have being born the same month and day of the year. So not necessarily the same year, but just same month and day. And I remember at the time thinking that would have to be something like 150, perhaps something like slightly less than half of the number of days in a year. And when he told us the question, he greatly surprised me. One of the reasons why I decided to tackle this problem. And after just like a couple of people, he proved his point in that session. And so for now, you guys will know that the answer is pretty small. So the formal question is, what is the minimum number of people that you need at a party in order to have a greater than 50% chance of two people having the same birthday? And in order to tackle this problem, I had to come up with a couple of simplifying assumptions in order to make it slightly easier. The first one is that there are no leap years. Every year has 365 years. We're going to ignore all the people that were born in February 29th will unfortunately have to be ignored. We're also assuming dependence of births. So that means no twins and triplets as that condition, and that would make the problem probably more difficult even if I did not try to tackle that. And finally, that birthdays are uniformly distributed over the year. I did some quick research on that, and apparently most people are born, there's a greater likelihood that people will be born 9 months after the holiday. So September is actually the most popular, it's the most common month for births. I think it's like a 6% chance, it's 6% more likely that someone will be born in September, but don't quote me on that. But so these are the assumptions. So in order to tackle the problem, the first thing that I realized and noted is that if I have more than k people in a room, more than 365 people in a room, the probability will obviously be 100%. And that is the case because if you have more people than days in the year, then inevitably at least there will be at least one pair of people that will share a birthday. And so in order to go further along with the problem, similarly to how we've done with many other problems throughout the year, I decided to think of the complement. So actually finding the probability that there are no matches between people. And I started off with a simpler case with assuming that k is equal to 3. So in that case, the first person, the person can be born in any of the 365 days of the year. However, the second person there's only 364 days to be born in order to make sure that they are not born on the same day as the first person. And consequently, the third person has only 363 days, since considering that 2 other days have already been taken. And then I did that number divided by all the total possibilities, and that gives me the probability that there's no match. This fraction comes to about 99.18%, meaning that there's a very small likelihood that with only 3 people in the room, 2 of them would have the same birthday. So in order to tackle the problem, I decided to do this with a spreadsheet. And the way that I did this, so just before I start, so numerator here, I have a function. Let's see this actually. So numerator. So just before we set this up, and I have, so the numerator is going to be the product of the numbers. So I'm just going to highlight here all this, and then number of terms is just going to count how many columns I have filled in. A consequent probability of no match is just going to be numerator divided by 365 to the power of how many people are in the room. And 1 minus b is obviously just 1 minus the other. So that should be pretty straightforward. So let's start and try to figure out what our answer would be. 364, 363, And now we can just drag and let's see. So with 9 people, you can see that there's a 46% chance, so a little bit far away from 50. We take it up to 15, that's almost there, it's a bit over halfway. So I wonder what it's gonna get. So we take it down to 20, we're at 41.14, that was a pretty fast growth. And then we go to 22, 47.57. Oh, that's not what I want. And then we take it down to 23, and that's 50.73. So we can see that with 23 people in the room, there's a 50.73% chance that one pair will share the same birthday. And actually the intuition behind that is that with 23 people, when you do 23 choose 2, that's actually 253 pairs of people, which enough pairs should push the probability of a match happening above 50%. So that's actually the reason, because we have to think that it's actually pairs. Some people to think that it's like, sometimes you find it odd. I guess at the time at Deloitte, I thought this was odd because I was thinking like, what is the likelihood that someone was born the same day as me in a room? But it's actually just any 2 people in a room, leading to a very large number of pairs of people. And just to finish this off, I counted, actually went to kind of how many people are in our class. It's 31. So when you, so I went here on my model. If I take this all the way to 31, we can see that it's actually 70. So there's a 73.05% chance that there'll be at least one pair of people in our probability class that will have the same birthday. So I guess now an interesting question to be considered for the future would be, then what is the probability that Professor Huber will be calling those people on the day of their birthday by rolling the dice? Well, but that's all for today. Thank you for listening.